Hey everyone, welcome to the Space Channel. Most people are aware that once astronauts leave Earth, they are exposed to hazardous space radiation. For many of us, radiation brings to mind Chernobyl, nuclear weapons, and other Earth-based sources. However, space radiation is actually quite different from what we encounter here on Earth. So today, I'm going to explain how space radiation differs from, say, the radiation from Chernobyl. Fortunately, in everyday life, most people only encounter radiation through high school physics and the countless movies about the Chernobyl disaster. In physics class, we were taught that there are three types of radiation: alpha radiation, a stream of helium nuclei; beta radiation, electrons; and gamma rays, photons with very high energy. All of these are produced during the decay of radioactive materials like uranium, thorium, and many other radionuclides. And they're extremely dangerous. Because the school curriculum is framed in this way, many people end up with an inaccurate picture of what radiation actually is and where it comes from. From a precise physics standpoint, radiation is any stream of particles capable of ionizing matter as they pass through it. For a particle to ionize matter, it has to carry a tremendous amount of energy, and nuclear decay is just one possible source of that energy. So alpha, beta, and gamma radiation are only some of the types of radiation out there. In physics, we group all such particle streams under the umbrella term ionizing radiation. In space, a large share of the radiation is gamma radiation, which isn't much different from what we get from radioactive sources on Earth. There are also streams of certain charged particles that simply can't be produced on Earth at all. Let's break down each of these types of radiation one by one. Gamma rays are produced in nuclear and thermonuclear fusion reactions, as well as when particles annihilate with their antiparticles. So their primary sources are stars and chunks of radioactive material. There's no fundamental difference between gamma rays of different origins. They differ only in energy. Additionally, Earth's magnetic field provides no protection against gamma radiation, and the atmosphere offers only weak shielding, allowing these rays to reach the surface and become part of the natural background. In other words, cosmic gamma radiation is essentially the same as the gamma radiation that constantly surrounds us, except for the higher maximum energies involved. Across most of the solar system, the intensity of gamma radiation is so low that it doesn't cause significant harm to living organisms. For gamma radiation to seriously harm the body, you'd have to be close to a supernova, a quasar, or another cosmic gamma ray source. The second type of space radiation is streams of charged particles. Only about 6% are helium nuclei and 1% are electrons, that is, alpha and beta radiation, while 92% are protons, which aren't emitted in nuclear decay, and therefore are absent from ordinary terrestrial radiation. These streams form because stars eject massive amounts of matter from their surfaces, which gets accelerated by their magnetic fields and sent off traveling through space. These outflows from stars are called stellar wind. For example, the Sun ejects several million tons of material per second this way. These particles carry far more energy than ordinary alpha and beta radiation from Earth-based sources and are much more damaging. Because of their large size and relatively low speed, ordinary alpha radiation primarily harms the skin and doesn't penetrate deeply into the body. You can block it with a piece of metal just a few millimeters thick. Beta radiation penetrates the body much more easily, and shielding against it takes a metal layer a few centimeters thick, about as thick as a wall in a house. But for cosmic rays, none of that is a serious barrier. They punch through even thick metal, though it does reduce their flux. These particle streams pass straight through the human body and cause damage in cells throughout. We don't really feel the effects of these rays on Earth because our magnetic field and atmosphere protect us. But in near-Earth orbit, they dominate. There are also the so-called galactic cosmic rays. Like the stellar wind, they're streams of various charged particles. but they're accelerated by different mechanisms to speeds far higher than anything the sun can produce. These acceleration processes are called Fermi mechanisms. They're complex, not fully understood, and would take a whole series of videos with heavy math to explain. Because of them, galactic cosmic rays sometimes seem to break the laws of physics, moving at speeds that defy easy explanation. This type of radiation dominates in interstellar space, and it can punch through the sun's magnetic field into the solar system, making a significant contribution to the overall radiation background. The farther you are from the sun, the stronger it gets. Beyond that, there are even more exotic forms of space radiation, though they're much rarer. Even neutrinos, which barely interact with matter, can deliver a dangerous dose, but only near an exploding supernova. That's all for now. If you enjoyed the video, please hit the like button and subscribe to our channel. See you next time.